200,000 miles away from Earth, a loud bang echoed through the command module. Within minutes, the crew looked out the left window to see their oxygen venting out into the void. They were losing electricity, light, and water. The three men were trapped inside a freezing metal cabin, traveling at 25,000 miles per hour in the wrong direction. Only days earlier, this mission had launched into a climate of public indifference. Lunar landings had become so common that major television networks stopped broadcasting the journey live. This raises the central question of the disaster. How did the agency that built the Saturn V find itself paralyzed by one electrical fault? Survival depended on the crew's ability to reverse engineer a multi-billion-dollar mission into a lifeboat. The Apollo 13 setup utilized a three-part architecture: the cone-shaped command module, the cylindrical service module, and the spider-like lunar module. The service module was the powerhouse, containing main engines, primary oxygen, and fuel cells. The explosion effectively killed the service module, forcing the crew to retreat into the lunar module. Its aluminum walls were so thin, roughly the thickness of 3 layers of kitchen foil, that a stray boot could have punctured the hull. The team faced a brutal math problem. They had to sustain 3 men for 4 days inside a vehicle designed to support 2 men for 48 hours. Reaching the moon was no longer the objective. The mission had become a zero-sum equation of power, time, and oxygen. The first crisis involved their trajectory. To return home, they had to fire the lunar module's engine, but the weight of the attached dead modules shifted the center of gravity, throwing the entire craft off balance. The crew had to execute a 35-second burn, using controls that now functioned backward. If the pilot tried to turn left, the craft pitched up. If he pitched down, it drifted right. Even after correcting their path, they were on track to run out of battery power long before reaching Earth, unless they made radical energy cuts. Flight controllers ordered the crew to shut down the guidance computer, their only navigation tool. Inside the cabin, temperatures dropped below freezing, and the men were restricted to drinking only 6 ounces of water a day. This triggered a third crisis. As the men exhaled, carbon dioxide levels rose to toxic levels, and the lunar module did not have enough chemical filters to scrub the air. The command module had spare filters, but they were square. The lunar module's air filtration system was built to only accept round canisters. Engineers on the ground spent hours designing a fix using only what was on board. They radioed the instructions to the crew, who built a functional adapter out of plastic bags, cardboard, and duct tape. Each technical solution seemed to reveal a new biological or mechanical limit, turning the spacecraft into a high-stakes test of human endurance. While the crew fought these symptoms in space, the root cause was a single oversight that occurred years earlier in a factory on Earth. During a design modification, the voltage for the oxygen tank heaters was raised from 28 volts to 65 volts to meet new spacecraft specifications. The thermostatic switches intended to shut those heaters off were never upgraded to handle the higher voltage. During a final ground test, the excess heat melted the protective Teflon insulation, creating the short circuit that would eventually trigger the explosion. The crew faced the hazards of deep space because of a forgotten administrative lapse on a factory floor. The final hurdle was the re-entry corridor. To land safely, the craft had to hit the Earth's atmosphere at an angle between 5.5 and 7.5 degrees. With the guidance computer still powered down, the crew steered the craft manually. They had to keep the Earth centered in their window to maintain the correct angle. As they hit the atmosphere, the heat created a plasma field that blocked all radio signals. This blackout lasted 4 minutes, a minute longer than anyone in Houston anticipated. The silence finally ended when the crew confirmed they were safe. Minutes later, their parachutes deployed for a successful splashdown in the Pacific. NASA later called Apollo 13 a successful failure. It demonstrated a team's ability to solve a series of cascading mechanical breakdowns using only the limited materials found inside the cabin. The mission highlights a persistent tension. While crews can adapt to sudden failures in real time, the spacecraft remains vulnerable to the blind spots built into the original blueprints. Today, as private corporations design systems for Mars that are significantly more complex than those of the 1970s, the question remains, is there another 28-volt error waiting in the